welcome to the third chapter or the module of this course, properties. In this module, we are going to cover the concept of pure substance and basic phase diagram, physics of phase change processes, and in general, how to obtain thermodynamic properties from the different tables which are usually given in the textbook. So, we are going to make use of thermodynamic property tables to solve problems. So, later we are going to define the ideal gas equation of state, equation based property evaluation, and hopefully that will give a lot of understanding to thermodynamic systems. So, let us first start with what is a pure substance. Pure substance is a substance that has a fixed composition. So, you can consider air which is composed of oxygen and nitrogen mainly, and still it is a uniform in composition, and hence it will be considered as a pure substance. Water can form in a liquid and vapor and as well as solid, but considering water in the form of, let us say, liquid vapor form together can be considered as a pure system because the composition is not changing. So, liquid composition is still the water, only one species, and as well as the vapor. So, this is an example here again. So, nitrogen and the gaseous air are pure substances. Water again, as I was mentioning, even though there are two phases, vapor and liquid, still considered to be pure phase because it has uniform composition. On the other hand, if you consider air in liquid and vapor, they are not pure substance because the vapor composition would be different from liquid composition because of different species involved in air. So, thus this system is not a pure system. On the other hand, a uniform composition of air, gas would be a pure system. Now, pure substance can be seen in different phases, and what we call phase is what we observe, let us say, in water, ice, liquid water, and as well as water vapor. Now, this is mainly because the substances are composed of atoms or molecules, and they have relatively different arrangements in different states. So, for the case of solid, they are placed, the molecules are placed in a lattice and they oscillate at the lattice position. So, this is a, let us say, lattice position. They oscillate around this position and they are composed in such a fashion that all attractive and repulsive forces maintain them at the relative constant distance from each other. So, it is all perfectly balanced and they are at the lattice point, but they oscillate around its lattice point. But you heat up a little bit and they can change their forms. So, for example, they can change from a very ordered structure to something which is not so ordered like liquid. Here the molecules tend to have more kinetic energy because it can now translate. It is not oscillating around this point, its own lattice point, but is translating in the medium. Beside that, each molecules do have some surrounding atoms or molecules together, and it has a certain structure. Solid has structures, liquid has structures, but as you further increase the temperature and make it a gaseous form, they apparently move quite random. Okay, there is no specific atom or molecule around each of them together. On the other hand, there is a group of molecules in the liquid phase which move each other in the liquid phase. So, there is a specific structure here, there is a specific structure here. The structure gets lost once it goes to the gas phase, and because of the low density they do not see too much each other, and there is no way it can come together and form a local ordering such that they can form a group and move together. So, it has a very low structure or structureless, the gas. So, these are the different forms of the phases. Now, we will take an example of how does the phase change during a process. You can heat up the water and convert to liquid. So, let us get a little bit more technical about it. So, let us consider water at 1 atmosphere and 20 degrees Celsius. Now, in such case the water exists in the liquid phase. So, at room temperature, which you will see water as a liquid phase, it will not immediately vaporize. You need to heat it up at 1 atmosphere. You need to heat it up such that it goes to 100 degree. Okay, and here the state of the liquid is that it is ready to vaporize. Now, this particular state will be called saturated liquid. The reason being that now this liquid is at equilibrium with its own vapor. It is about to vaporize. So, the word saturation would be used for such state or such a condition. Okay. So, it is something like liquid is saturated with its own vapor, but this occurs at a specific condition. For the case of 1 atmosphere, it occurs at 100 degrees Celsius. For if you change the pressure, the temperature will be changed. So, this particular state where you consider the 1 atmosphere and 20 degrees Celsius is sometimes also called compressed liquid. This is a liquid which is not going to vaporize, okay, at this condition. They are called compressed liquid because at T equal to 20 degrees Celsius, if you want to vaporize, you need to reduce the pressure, and this pressure which you want to reduce 2.3392 kilopascal. So, if you want to keep the temperature fixed and you still want, if you want to vaporize it, then you need to reduce the pressure to such a conditions, and at this point it will vaporize. So, this pressure at 1 atmosphere is much higher than this pressure. This is much higher than 101.325 kilopascal, which is our 1 atmospheric condition, which essentially means this particular liquid is compressed, because you have increased the pressure at 20 degrees Celsius. So, that is why it is also called compressed liquid. So, essentially at 20 degrees Celsius, this P sat, saturation pressure, at P equal to 1 atmosphere, the saturation temperature is T sat is 100 degrees Celsius. This is also sometimes called subcooled liquid, because the temperature to vaporize for 1 atmosphere is 100 degrees Celsius. So, this T 20 degrees Celsius is lower than 100 degrees Celsius, is lower temperature than the saturation temperature, and thus it is subcooled liquid. So, let me again summarize this. The compressed liquid is a substance that is not about to vaporize. Saturated liquid would be a liquid that is about to vaporize. Okay, what about saturated vapor? A vapor that is about to condense. So, instead of taking liquid, if you have taken vapor and you change the variable temperature and pressure such that it is about to condense, then it will be a saturated vapor. So, we will talk about this more illustratively. So, now what was the state 1 was compressed liquid, state 2 was that liquid was ready to vaporize. Okay, now I am further heating up. Now, what happens that the certain molecules of the liquid is transferred to the vapor state. So, the liquid volume is also changing. This is the liquid volume, this is the vapor. So, the liquid volume is changing at this condition. Since this is 1 atmosphere, this is at equilibrium with this phase is at equilibrium with this phase. That is why it is called the saturated system. It is saturated with liquid and as well as vapor. So, liquid and vapor are at equilibrium. So, this is the state 3. You further increase when all the liquid is converted to vapor completely. But at this point, if you slightly change the variables, then it can also convert back to liquid. So, this is the condition, the temperature remains still constant. So, remember the temperature is constant. Heat here is being used to change the liquid to the vapor. Once the complete vapor is formed, then further the temperature will rise. So, now you further heat it up, you get a state which much higher temperature, which is 300 degrees Celsius. So, as more heat is transferred, the temperature of the vapor starts rising. In this condition, you have superheated vapor. So, you have 3 states which we talked about. One is a saturated vapor, a vapor that is about to condense, which is state 4. Saturated liquid vapor mixture, the state at which liquid and vapor coexist, which is of course this is state 3, and the superheated vapor, a vapor that is not about to condense. So, superheated vapor is a vapor that is not about to condense, which is state 5. So, we can plot this in a temperature specific volume diagram, and so let us go back again. State 1. State 1 was compressed liquid. It was at 20 degrees Celsius at 1 atmosphere. We are keeping the pressure fixed. The pressure is based on this weight here, piston. So, the weight is fixed, so pressure is fixed. So, you heat it up, so you get from 1 to saturated liquid 2, and then saturated liquid to saturated vapor here, and the intermediate point are all saturated mixtures of different composition of liquid and vapor. and then after it reaches this saturated vapor, the temperature goes up, okay, and the superheated vapor is achieved. Now you remember this flat region. This flat region is where your temperature is fixed, which is 100 degrees Celsius. So this temperature is your Tsat. It's called saturated temperature corresponding to pressure of 1 atmosphere. So if you change the pressure, you're going to get different saturation temperature. So if you increase the pressure, you may get different one. And this is something which we are going to talk or describe a little more. So this is how it is. So again, going back to the values of the water. So this is temperature. Again, this is a specific volume. And earlier we talked about 1 atmosphere, very close to 0.1 megapascal. This was, we were heating from compressed liquid case to saturated liquid and then further to saturated vapor and then superheated vapor. Now if you change the pressure, so for example if you change the pressure to lower value such as this case P equal to 0.01 megapascal, what do you see? You see that there is a positional change of saturated liquid and vapor. So saturated liquid is shifted to the left, saturated vapor is shifted to the right, the volume is shifted. So you see the vapor volume is more, the liquid is less, right? Or in other words, this difference is more at a lower pressure, and then this difference between these 2 points is decreasing as you increase the pressure. And at certain point, these 2 points coincide. The 2 points are the saturated liquid and saturated vapor. And this particular point, you cannot distinguish saturated vapor and liquid. So this is the point which we call it critical point, where there is no phase separation. The phases cannot be separated. It is all homogeneous. Okay, so this critical point is associated with all the systems, all the substances. So for the case of water, it is the critical point is 373.9.95, and once you fix this temperature, the pressure is also fixed because it occurs at a specific point. Here the pressure is 22.06 megapascal. You can connect this point like this and you can come up with a phase diagram. So this becomes the phase diagram. So in other words, what you are doing is you are plotting this and you are generating this like kind of plot, where this each point corresponds to a specific saturated liquid and saturated vapor. So this is your saturated liquid and this is your saturated vapor, and this is your critical point. So okay, so this has a specific critical point we are going to denote as Tc, critical temperature, and critical pressure. Okay, so let's and what about the other states? This one, for example, which is 25 megapascal. Well, we do not see any phase change at all because this is a region of supercritical point. So you are going from compressed, this is a compressed liquid, and this is a supercritical region. So this would be a supercritical region. So this we can put it in a simpler form now. So again, this is the temperature and volume. This is in general, it's not just related to water now, it is a general phenomena that a liquid undergoes change if the pressure is less than P critical and temperature is less than T critical. And then at a certain point there is no further, you cannot separate the phase, that will be the critical point. So if P is greater than P critical, then there will be no phase change. There is a inflection point at Tc and Pc. So the critical point is the point at which saturated liquid and saturated vapor states are identical, which means you cannot distinguish. Okay. So at supercritical pressure, there is no distinct phase change process. Okay. That means there cannot be a boiling at supercritical process. Such kind of phase change depends on pressure and temperature, as already we can infer from our discussion. For example, your water boils at 100 degree Celsius at 1 atmosphere, but water boils at a lower temperature when you go to mountain. Okay. So why is that? So let's first look at it again. So what is the saturation temperature? The temperature at which pure substance changes phase at a given pressure. What is the saturation pressure? The pressure at which pure substance changes phase at a given temperature. So, can we find out this T sat and P sat for the case of water? So, let us go back. So, this line was for P equal to 0.01 megapascal, this was your T sat at P equal to 0.01 megapascal, and similarly this will be your T sat at P equal to 1 megapascal, okay, and similarly it will be T sat at P equal to 15 megapascal. So, what we see? We see that as you increase your pressure of the system, the saturation pressure increases. There is another thing which we should see. This difference between this point, the saturation liquid and saturation vapor, it is decreasing, and we know that you need to provide energy to convert liquid to vapor. So, in a sense the vapor energy is larger than the liquid energy. So, difference between them is going to be latent heat of vaporization. It is a change in the internal energy, because latent heat is part of internal energy. So, this is latent heat of vaporization. Latent heat of vaporization decreases as we increase the temperature and pressure, you can clearly see, because these differences are smaller. Okay. So, based on this analysis you can clearly understand that the pressure as a function of T sat should look like this, and this is the reason that if you reduce the pressure, the temperature will be lower. So, if you reduce the pressure from 100 to somewhere here, the corresponding pressure will be less. It will not be 100 degrees Celsius for the case of water, as in the case in the mountain. So, as you say, this, if you fix the pressure, this will be the temperature at which it will boil. You reduce the boiling temperature, T boiling temperature reduces, okay, and that is the case what we see in the case of when you go to mountain and start heating up.
Okay, that will be the end of this lecture, where we have introduced the concept of pure substances and discussed the phase change of pure substances. We have illustrated the PV, TV and some property diagram. We will continue with this discussion in the next lecture, where we will discuss more about the property diagrams, and in particular we will look into the PVT surface of pure substances. We will also introduce property tables later on, where we are going to use the tables to solve some relevant problems, and later on in this particular module we will introduce equation of state and the commonly used equation of state. So, see you in the next lecture.